For decades, the image of nuclear power has been singular, a massive concrete cooling tower looming over a landscape, demanding billions of dollars and decades to build. The reactor of the future looks completely different. It fits inside a standard shipping container. Heavy industry and modern technology have developed an insatiable appetite for zero-carbon, baseload electricity, and they increasingly need it deployed in remote locations, far away from traditional centralized infrastructure. Right now, our most advanced manufacturing and computing facilities are tethered to an aging power grid. That reliance creates a massive point of failure for the entire economy. Wind and solar arrays are intermittent. They drop off when weather changes, meaning they simply cannot sustain the continuous, high-density energy required to run a steel plant or a hyperscale data center 24 hours a day. Controlling the industries of the 21st century means securing power that never blinks. The geopolitical advantage belongs to whoever can deploy city-scale electricity on demand, anywhere on the map. The engineering solution currently in development across 127 global designs is the Small Modular Reactor, or SMR. An SMR is an advanced nuclear reactor with a power capacity of up to 300 megawatts per unit, designed to be manufactured in a factory rather than constructed on site. This plunging trendline shows the effect of economies of scale. Pumping identical units off an assembly line quickly drives the cost per megawatt down. By treating reactors like commercial products rather than custom megaprojects, manufacturers are applying the exact same economic logic that eventually made solar panels cheap. The urgency to deploy them is being driven heavily by artificial intelligence. AI data centers already consume 3% of all global electricity, an amount equal to the entire country of Japan, and that consumption is projected to double in the next 10 years. To feed that demand, tech giants are circumventing the public grid entirely. X-Energy has formed alliances with Amazon, Korea Hydro and Nuclear Power, and Doosan Enerbility to build dedicated nuclear installations specifically to run AI computing centers. These new installations rely on a design feature called a passive safety system. This is an engineering mechanism that uses physical laws like natural convection and gravity to cool the reactor indefinitely, without requiring human intervention, external electricity, or extra water. For the world's largest tech companies, adopting nuclear technology is a calculated business maneuver. They are securing absolute corporate energy sovereignty to ensure their operations can never be throttled by a strained public grid. The civilian sector is moving fast, but the military calculus is even sharper. Operating a modern army requires a massive logistical tail, leaving forces highly exposed if their fuel lines are attacked. Right now, military outposts require trucking thousands of liters of highly combustible diesel and kerosene through active conflict zones daily, simply to power radar systems and keep the lights on. To sever that logistical tether, the U.S. Army and the Pentagon have launched Project Janus and Project Pele. These initiatives are slated to deploy mobile micronuclear reactors to military bases by 2026 and 2028. These military-grade reactors are scaled down even further to the 5 to 15 megawatt range. A megawatt is a unit of power equal to 1 million watts, and 15 of them is exactly the amount needed to run an off-grid defense installation indefinitely. By airdropping one of these self-contained units into a forward operating base, commanders instantly eliminate the need for daily fuel convoys. Energy that cannot be blockaded or embargoed changes the math of engagement. When an outpost generates its own continuous baseload power, a severe logistical vulnerability becomes a massive tactical advantage. Engineering a smaller reactor does not erase the physical realities of splitting atoms. This technology carries severe, unresolved complexities. Like their massive predecessors, SMRs still produce long-lived radioactive waste. Early studies suggest some miniaturized designs might actually generate more radioactive waste per unit of electricity than a conventional legacy reactor. And while the private sector is moving at breakneck speed with over 100 different prototypes in development, global regulatory frameworks and long-term waste storage policies are lagging years behind. Public trust in nuclear safety remains incredibly fragile. Scaling this technology globally means these waste management and regulatory hurdles have to be actively solved alongside the engineering, rather than treated as an afterthought in the rush to secure power. If you look closely at history, every major leap in industrial production was triggered by a specific transition in how we generate energy. Factories multiplied when we harnessed steam to run physical machinery. global logistics and mass transport scaled aggressively with the extraction of oil, and modern manufacturing spread across the globe riding on the back of the centralized electric grid. The foundational hardware for the next era of heavy computing and mechanized warfare is being locked in right now. The organizations and nations that will dictate the rest of the century are the ones securing power from atoms the size of a single room.